It began as a whisper in the data, a flicker of light that shouldn't have been there, hidden in the deep, cold archives of the early universe. At first, the engineers at the Mission Control Center dismissed it as an artifact, a momentary glitch in the infrared sensors, or perhaps the ghostly trail of a stray cosmic ray piercing through the shielding. But then it happened again, and again, and again. It was as if the universe itself was trying to send a message, one that defied every single rule we had written in our textbooks for the last half-century. We were looking for the dawn of time, searching for the first faint embers of the earliest stars, but what we found instead was a nightmare for modern cosmology. We found galaxies that were too big, too bright, and entirely too mature to exist in the infancy of the cosmos. It was as if we had opened a door into a room we were certain was empty, only to find a bustling, crowded party already in full swing. This is not just a story about a piece of glass and gold floating a million miles away in the dark. This is the story of a fundamental crisis in our understanding of reality, a moment where the bedrock of our knowledge began to crack. Welcome to the edge of what we think we know. For decades, the standard model of cosmology, the Lambda CDM model, has served as our map of the universe. It describes a cosmos born from the Big Bang, expanding outward, cooling down, and slowly, painstakingly building structure over billions of years. It tells us that gravity acts like a slow-motion glue, pulling gas and dust together to form the first stars long after the fog of the early universe cleared. But when the James Webb Space Telescope opened its golden eye, it looked back across 13.5 billion years of time and saw something that shattered the script. It saw massive, fully formed galaxies swirling in the darkness, teeming with billions of stars, existing at a time when they should have been nothing more than wisps of primordial hydrogen. These are the impossible objects. These are the galaxies that should not exist. And as we peel back the layers of this mystery, we find that the problem isn't just about the telescopes or the sensors. The problem is that the universe is refusing to play by our rules, and we are forced to confront the possibility that everything we thought we knew about how the universe evolved might be wrong. To understand why this is such a shock, we have to travel back to the late 20th century, to a time when our vision of the cosmos was defined by the legendary Hubble Space Telescope. Hubble was a miracle of engineering, a window into the deep past that allowed us to see galaxies billions of light-years away. It was our primary tool for measuring the age and expansion rate of the universe. We spent 30 years refining our models, building simulations that predicted the growth of the universe with incredible precision. We knew the timeline: Big Bang, followed by a dark age, followed by the first faint flickering of stars around 400 to 500 million years after the beginning. We were confident. We had the evidence. Or so we thought. The consensus was so strong that it formed the foundation of almost every PhD thesis and research paper written in the field for a generation. We felt like we were nearing the end of the book, polishing the final chapters of cosmic history. But the universe has a way of humbling those who believe they have mastered its secrets. When the James Webb Space Telescope was first conceived, it was sold to the world as the successor to Hubble, a more powerful, more sensitive machine designed to peer through the thick, obscuring curtains of cosmic dust. We expected it to find the first stars, the faint, isolated pinpricks of light that marked the transition from darkness to light. We designed its optics to capture the long wavelength infrared light that has been stretched by the expansion of the universe as it traveled across the void. We built it with a massive, folding gold-coated mirror, a feat of mechanical engineering that bordered on the impossible. We launched it into the cold, silent depths of Lagrange Point 2, a lonely orbit far from the heat and light of our own planet, where it could stare into the deepest shadows of the abyss. For months, we waited as the mirror unfolded, as the heat shields deployed, and as the cooling systems brought the instrument down to temperatures near absolute zero. When the first images finally came back, they were breathtaking. The sheer detail was unlike anything we had ever seen. But hidden in the noise of those glorious, high-resolution snapshots was the data that would eventually bring our house of cards crashing down. The primary culprits behind this scientific tremor are the candidates for the most distant galaxies ever observed. When our automated pipelines processed the light spectra coming from these distant, ancient blobs of color, the redshift readings were off the charts. Redshift is the cosmic tape measure. Because the universe is expanding, light from distant objects gets stretched, shifting from blue toward the red end of the spectrum. The more distant the object, the greater the shift. When the analysis came back for these specific galaxies, the values indicated that we were seeing them as they existed mere hundreds of millions of years after the Big Bang. In the standard model, galaxies at this stage should be tiny, chaotic, and barely formed, proto-galaxies, just beginning to aggregate. Instead, what we saw were massive, bright, structured systems that rivaled the size and light output of our own Milky Way. Imagine looking at a high school yearbook and finding a photo of a fully grown, gray-haired man sitting in a kindergarten classroom. It doesn't make sense. The timeline is physically impossible based on our current calculations of how dark matter collapses and how gravity builds large structures from cold, inert gas. This isn't just a minor discrepancy or a rounding error in a spreadsheet. This is a fundamental challenge to the rate at which structure forms in the universe. Our models say that it takes time, immense, agonizing amounts of time, to build a galaxy of this magnitude. You need to gather enough mass, you need to trigger the fusion of hydrogen into helium, and you need to clear away the debris of the formation process. This process has a set velocity, restricted by the density of the universe and the behavior of dark matter, which is the scaffold upon which all visible matter is hung. If these galaxies are already this mature at such an early epoch, then either our understanding of how stars form is fundamentally flawed, or our understanding of dark matter is incomplete, or perhaps, most terrifyingly, the Big Bang model itself is missing a massive, unknown component. We are looking at a cosmic anomaly that requires us to rethink the physics of the early universe from the ground up. As the data from the early observing cycles began to circulate, the community of astrophysicists was split into two camps, the skeptics and the believers. The skeptics argued, rightfully so, that we were misinterpreting the data. Perhaps these galaxies weren't as massive as they seemed. Perhaps the light was being lensed by intervening foreground galaxies, which can magnify the appearance of distant objects, creating an illusion of size and brightness. Maybe there was a dust population that we weren't accounting for, which could mask the true nature of these systems. The arguments were fierce, played out in seminar rooms and on the pages of journals like Nature and Science. Yet, despite the pushback, despite the rigorous efforts to find a conventional explanation, the signal persisted. The galaxies were there. They were massive. And they were ancient. The data refused to go away. It was as if the universe was pointing a finger directly at us and saying, "You missed something crucial." This brings us to the core of the dilemma, the tension between observation and theory. For years, we have relied on a model that fits the data perfectly, as long as we don't look too closely at the very first moments of the cosmos. It's a bit like a map that is accurate everywhere except for the forbidden zone where we haven't explored yet. We assumed the map was a perfect representation of reality. Now, we are standing in the forbidden zone, holding a compass that is spinning wildly, unable to find north. What if the universe started differently than we thought? What if there were mechanisms for star formation that were much more efficient in the early universe, fueled by conditions we can't even imagine today? What if our measurement of the expansion rate of the universe, the famous Hubble constant, is skewed, suggesting that the clock we use to measure the age of the universe is running faster than we realized? Every single one of these possibilities leads to a cascade of further questions. If we change one variable, we risk unraveling everything else. If we make the universe younger to accommodate these galaxies, we run into trouble with the age of the oldest stars we find in our own galaxy. If we change the way dark matter behaves, we have to rewrite the equations that govern the motion of all visible matter in the cosmos. We are currently living in a state of scientific limbo, caught between the certainty of the past and the impossible clarity of the present. And the most startling part? This is just the beginning. The James Webb Space Telescope is only one instrument, and its mission has only just begun to scratch the surface. We have years of observation ahead of us, with cameras and sensors that are currently trained on targets we couldn't even see a year ago. We are essentially watching the foundations of modern physics begin to tremble. It is an exhilarating and terrifying position to be in. In the history of science, whenever we have encountered such a fundamental crisis, it has always heralded a paradigm shift, a moment where our entire worldview is reorganized to account for new, uncomfortable truths. Think of the transition from the geocentric model of the solar system to the heliocentric model, or the shift from Newtonian mechanics to the relativistic physics of Einstein. In each case, it required the courage to look at the facts, even when they contradicted the long-held beliefs of the day. Today, we are staring into the mirror of the deep past, and we are seeing a reflection that we do not recognize. We are seeing a universe that is far more energetic, far more creative, and far more complex than we ever dared to imagine. The question is no longer whether our models are incomplete, but rather, what are we going to replace them with? As we delve deeper into this enigma, we have to ask ourselves, what exactly is the mechanism that allows these galaxies to flourish so quickly? Is there a new kind of physics lurking in the shadows of the early universe, something that doesn't involve the standard particles we've spent decades documenting at the Large Hadron Collider? There are theories involving primordial black holes, early cosmic magnetic fields, and even dark energy fluctuations that could have acted as a catalyst for this rapid growth. Each of these theories is a thread we must pull, hoping that it unravels the right part of the tapestry. But pulling these threads also means risking the integrity of the whole, and the scientific community is understandably cautious. We are in the middle of a high-stakes investigation, one where the evidence is trillions of miles away and the truth is hidden in the interference patterns of ancient light. We are forced to confront the idea that the universe might not be as homogeneous as we once thought. For a long time, we operated under the assumption of the cosmological principle, which states that on a large enough scale, the universe looks the same in every direction. But if these galaxies are everywhere, if they are the norm rather than the exception, then the universe was incredibly lumpy, incredibly structured, and incredibly active from the very first moments of its existence. This would mean that the early universe wasn't a slow, cold soup that took eons to simmer into galaxies, but a chaotic, high-pressure environment that ignited almost instantly. How do we reconcile that with the cosmic microwave background, that ancient, uniform glow that tells us the universe started out in such a smooth, low-entropy state? That is the question that keeps theorists up at night. That is the bridge we must cross to get to the next stage of our understanding. And as we continue to collect more data, as we refine our measurements and sharpen our focus, we are beginning to realize that the answers might not be found in the refinement of our old models, but in the radical, uncomfortable acceptance of something entirely new. The journey toward understanding these impossible galaxies is just beginning, and the implications ripple far beyond the borders of astronomy. They touch on the very nature of existence, how matter comes together, how time manifests, and what the ultimate fate of this expansive, beautiful, and fundamentally strange cosmos might be. We have built our civilization on the promise of understanding our environment, and for a long time, we thought we had done it. We thought we had the universe figured out. But the golden eye in the sky has shown us that the map is wrong, the path is obscured, and the destination we were aiming for has shifted beneath our feet. We aren't just looking at stars, we are looking at the boundaries of our own ignorance. But what lies on the other side of that boundary? What happens when the physics we know finally breaks down completely, and we are forced to look at the wreckage and start building something else entirely? To find out, we have to look deeper into the engine room of the early universe, where the rules of gravity, light, and mass are currently being rewritten in real time. We are about to step into the heart of the crisis, to see what happens when the impossible stops being a theory and starts becoming the new reality of our cosmic perspective. The crisis of the impossible galaxies is not a localized glitch, but rather the tip of a cosmic iceberg that forces us to question the very architecture of the early universe. To understand how these behemoths could exist so early, we have to interrogate the invisible scaffolding that supports them, dark matter. In our standard models, dark matter is the silent architect. It is the cold, sluggish substance that clumps together first, creating gravitational wells that act like celestial traps, dragging in ordinary gas to build stars and galaxies. For decades, we have modeled this process as a gentle, incremental climb. We imagined a dark matter halo forming slowly, and then, only after reaching a critical density, slowly accumulating enough baryonic matter to ignite a galaxy. But if our new observations are correct, the timeline for this assembly is fundamentally broken. We are forced to consider if dark matter in the early universe was not cold and sluggish, but possessed properties we have yet to observe in our local neighborhood. Perhaps there is a component of dark matter that interacts with itself, or experiences forces that accelerated the collapse of these structures. This would be a profound departure from our established paradigm, shifting our understanding of the universe's invisible mass from a static, passive background into an active, dynamic participant that fueled the rapid formation of the first celestial structures. When we move beyond the dark matter dilemma, we confront the challenge of star formation efficiency itself. Even if the gravitational wells were ready, the conversion of primordial gas into a galaxy requires an astonishing level of star formation. The laws of physics dictate a certain limit on how fast clouds of hydrogen can collapse, fragment, and burn. These limits are derived from the cooling rates of gas, the speed at which a cloud can shed energy and condense. But the JWST data suggests these early galaxies were churning out stars at a rate that defies those theoretical constraints. We have to ask, what if the primordial environment was so radically different that standard stellar feedback mechanisms, the winds and radiation that usually quench star formation, were suppressed or entirely absent? Perhaps the very first generations of stars, the theoretical population 3 stars, did not behave like the stars we see today. If these early systems were dominated by massive, short-lived, incredibly bright stellar populations, they could outshine anything we have previously modeled, creating the illusion of a mature galaxy when, in reality, we are looking at a hyper-efficient, stellar birthing firestorm that burns out in the blink of an eye. This would be a cosmic paradox, a system that looks like an old, settled city, but is actually a chaotic, temporary construction zone that is already consuming its own future. We must also contend with the possibility that our standard yardsticks, the methods we use to determine distance, are built on flawed assumptions. The primary way we judge the distance of an object is through spectroscopy, measuring the degree to which its light has been stretched into the red part of the spectrum. But what if there is something in the intervening space that we don't fully understand? If there is an unknown medium, perhaps a form of low-density intergalactic plasma or a strange distribution of dark dust, that interacts with light in ways we haven't accounted for, it could be artificially reddening the light, making objects appear much farther away than they actually are. This is a controversial hypothesis, one that sits on the fringes of modern thought, yet it is a necessary line of inquiry when the alternative is rewriting the Big Bang. If we are miscalculating redshift because of an unrecognized property of the vacuum itself, the entire history of the universe as we have mapped it would require recalibration. It would be a realization that our cosmic depth perception has been skewed, leading us to believe that the horizon was further off than it truly is. Deepening this investigation, we arrive at the role of supermassive black holes. We have long viewed black holes as the denizens of mature galaxies, the anchors around which stars orbit. Yet, the data suggests that these black holes were present, active, and fully grown at the very beginning. We see evidence of quasars, monstrously bright, black hole-powered engines, glowing in the darkness of the high redshift universe. A black hole cannot simply appear, it must feed, grow, and consume over eons. If we see them early, it implies they grew at a rate that should be physically prohibited by the Eddington limit, which governs the maximum brightness and growth rate of a black hole based on the radiation pressure it exerts. If these holes were eating their fill and growing at hyper-accelerated speeds, it implies a fundamental oversight in our understanding of gravity and mass accretion. Are we seeing the remnants of a previous epoch of the universe? Or perhaps we are observing a unique type of direct collapse black hole, born from the total gravitational surrender of giant gas clouds, skipping the star formation phase entirely? This suggests a much more violent, high-speed beginning to the cosmos than the quiet, slow-motion evolution we previously championed. Consider, for a moment, the nature of the cosmic microwave background itself. We hold it up as the blueprint of the early universe, a map of density fluctuations that set the stage for everything that followed. But that map was created by the Planck satellite, measuring the universe in a specific way that assumes our standard model is correct. If the early universe was lumpy on scales we didn't account for, if there were topological defects in space-time, cosmic strings or domain walls, the initial conditions we've been using to run our simulations might be fundamentally inaccurate. These high-energy phenomena could have acted as gravitational seeds, sowing the universe with massive, ready-made galaxies in a process that bypassed the long, slow wait of the standard model. It is a terrifying prospect, for it suggests that the smooth beginning we see in the microwave background is a deception, a low-resolution blur that hides a much more chaotic, turbulent reality. We have reached a stage where we must perform a forensic audit of the universe's past. The discrepancies are no longer buried in the noise, they are the loudest signal we have. And as we compare these distant, problematic galaxies with the mature ones in our own local cosmic neighborhood, the differences are becoming starkly clear. The galaxies we see now are the result of billions of years of mergers, galactic cannibalism, and steady, predictable evolution. The galaxies we see in the early universe seem to have skipped all of that. They are singular, powerful, and isolated in a way that is profoundly unsettling. We are essentially looking at a picture of a newborn infant, yet the infant is wearing a suit, carrying a briefcase, and working a job. The developmental biology of this universe seems to be running on an accelerated timeline, or perhaps, it is following a different evolutionary path entirely. As we grapple with these anomalies, we find that the conversation is shifting from how can we fix the model to what is the model missing. We are seeing the rise of alternative cosmologies, models that incorporate varying constants of nature, modified gravity, or even cyclic universes that undergo infinite booms and busts. Each of these theories attempts to reconcile the impossible galaxies with the rest of our observations, yet each one introduces new, equally difficult challenges. We are finding that every answer we provide to one mystery immediately births three more. It is a recursive process of discovery, a tightening spiral that draws us closer to the center of the mystery. The technology at our disposal is no longer just a window, it is a diagnostic tool, and it is showing us that the patient is suffering from a massive systemic shift. We have spent decades building a house of cards, and now, the gentle wind of new data is blowing through the hallways. For some, this is cause for alarm, for others, it is the most exciting moment in the history of science. To be alive at a time when the fundamental laws are in question is a rare privilege. It is the moment when the history books are rewritten, when the scientists of the future look back at this exact period as the great pivot, the moment when the modern perspective finally collapsed under the weight of its own success. We are no longer waiting for the universe to explain itself. We are actively cross-examining it, forcing it to reveal the mechanisms it has kept hidden since the dawn of time. But if the physics we know is cracking, what is the nature of the forces that might be emerging in its place? We are sensing the presence of something deeper, something that connects the largest structures in the universe to the smallest particles in the quantum foam. Could there be a hidden coupling between the vacuum energy and the formation of galaxies that we have consistently ignored? We are beginning to realize that the vacuum is not empty, and that the energy density of the space between stars might be the key to understanding why the universe acted so differently in its youth. We are standing on the precipice of a radical new synthesis, where the cosmology of the large scale and the particle physics of the tiny might finally merge into a unified, coherent, and perhaps much more mysterious theory of everything. As we prepare to leave this layer of the investigation, we find ourselves with more questions than answers, but we have stripped away the comfort of the status quo. We know now that the galaxies are real, that their presence is a legitimate challenge to the core of our knowledge, and that our current explanations are beginning to fray. We have looked at the gravitational scaffolding, the star formation firestorms, the hyper-accelerated black holes, and the possibility of fundamental errors in our distance measurements. But this still leaves the most daunting question of all. If we are fundamentally wrong about the timeline of the universe, what does that mean for its ultimate destiny? How does the story end if it began so differently than we believed? To find the answer, we must move beyond the light of the first galaxies and venture into the dark, into the very mechanics of the vacuum itself, where the next evolution of our understanding is currently taking shape. We are about to cross the threshold into the deep theory, where the math of reality begins to blur into the unknown, and we will finally confront the possibility that the universe is not just breaking physics, it is outgrowing it entirely. If our established models of galactic maturation are truly inadequate, we must consider the possibility that we have been viewing the history of the cosmos through a distorted lens. We have traditionally relied on the assumption that the expansion of the universe is a smooth, continuous, and predictable event. We base this on the expansion rate, the Hubble constant, which has been the cornerstone of our cosmic narrative. But what if that expansion itself hasn't been as uniform as we assumed? If the expansion rate was punctuated by bursts of rapid, uneven acceleration in the early epochs, it could create the appearance of premature structure. This is not to say that the Big Bang did not happen, but rather that the expansion might have been characterized by a more complex, volatile geometry than the simplified, spherical model we rely on in our simulations. By treating the universe as a perfect, homogeneous sphere, we may be smoothing out the very wrinkles in spacetime that allowed for such rapid, early-stage galactic growth. The existence of these massive early galaxies forces us to confront the role of entropy in the infancy of our universe. We are taught that the universe moves from a state of low entropy, an ordered, smooth beginning, to a state of high entropy, where structure breaks down. These massive, complex galaxies appearing so soon after the dawn of time suggest a universe that was surprisingly organized, perhaps even structured, at its very inception. This forces us to entertain the idea of informational density. Is it possible that the early universe held a higher degree of initial information or coding than we realized? If the vacuum itself was programmed with higher density fluctuations, or if the distribution of mass was non-random from the moment of the Big Bang, then the formation of galaxies would not be a long-term evolutionary process, but an inevitable expression of initial conditions that we have yet to map. Beyond the macrostructures, we must examine the light itself. When we study these impossible objects, we are dealing with photons that have traveled across a distance so vast that they have been shifted into the infrared. We trust that our calibration of these sensors is perfect, but we are utilizing a technology that operates in a regime where the signal-to-noise ratio is constantly pushed to its breaking point. We are filtering out the foreground glow of our own solar system and the diffuse light of intervening galaxies to find these ancient pinpricks of data. What if some of these galaxies are actually something else entirely? What if they are dense, high-energy cosmic filaments, the connective tissue of the web of dark matter, that we have been misinterpreting as distinct, mature galaxies? If these are not localized cities of stars but rather the glowing nodes of a much larger, global network of dark energy interaction, then the entire premise of galactic maturity is built on a fundamental misreading of visual data. We must also pivot to the reality of the scientific community itself, which is currently undergoing a painful, necessary evolution. For years, the academic pressure to align with the standard lambda CDM model created a sort of intellectual inertia. It was safer to work within the established parameters than to suggest that the bedrock was crumbling. But the James Webb Space Telescope has democratized the crisis. Because the data is so undeniable, even the most traditionalist cosmologists are now being forced to adapt. We are seeing a shift in the philosophy of physics, moving away from top-down modeling, where we force the universe to fit into a preconceived box, toward bottom-up analysis, where we allow the data to dictate the laws, however strange or uncomfortable they may be. This is a move toward a more humble, data-driven cosmology that treats every new discovery not as an inconvenience to the old model, but as a potential breakthrough toward a more nuanced, sophisticated understanding of physical law. This brings us to the ultimate question of the multiverse versus the singular universe. If our physics are failing to explain our own reality, perhaps it is because our universe is not a closed system. Could the early formation of these massive structures be a sign of a high-energy interaction between our own nascent cosmos and another? Even for a brief moment in the inflationary period, a ripple or an intersection with another membrane of reality. It could explain the sudden, massive injection of energy and matter that seems to defy our conventional timeline. While this sounds like the realm of science fiction, it is becoming a valid mathematical line of inquiry as we find ourselves running out of conventional solutions. We are testing the limits of what one solitary universe can accomplish on its own, and we are finding that it may not be enough to account for the grandeur of what we see. Consider the role of time as a fundamental variable. We perceive time as a linear, absolute progression, but general relativity teaches us that time is malleable. It bends under gravity, it slows down at velocity. If the early universe was a region of extreme, localized, and heterogeneous gravity, is it possible that our concept of an age for these galaxies is relative? Could these systems have experienced a different flow of time during their initial formation phases compared to the regions we inhabit today? If time itself behaved differently in the high-energy soup of the early cosmos, then the 400 million years we measure might be a human construct, a relative calculation that doesn't capture the true, non-linear speed at which those early structures were able to assemble. We are trapped by our own temporal bias, measuring the universe against the clock on our wall, while the universe itself may be governed by a much more flexible, multifaceted temporal architecture. We must also look at the potential for new, non-standard particles. If we have been searching for dark matter for decades and coming up empty-handed, maybe it is because we are looking for a singular particle when we should be looking for a landscape. Perhaps the dark sector of the universe is just as complex as the baryonic, visible sector, filled with its own forces, its own interactions, and its own versions of light and atoms. If the early universe was dominated by these exotic, dark sector interactions, it would explain why galaxy formation was so rapid. It would be as if the universe were being built with a different set of materials, a more efficient construction kit than what we see in the current, cool, and dilute era. This is a humbling realization, that we are living in the aftermath of a much more creative, high-energy era, and that the universe we see today is just a quiet, cooling ember of a much more violent, productive wildfire. We are, therefore, forced to rewrite the story of our origins. The narrative of a slow, gradual evolution is likely a comfort-seeking myth. The truth, as revealed by the golden eye in the sky, is that the universe is far more capable of producing complexity and beauty than we ever gave it credit for. We are not the masters of the cosmic map, we are, at best, novice explorers who have just climbed the first hill and realized that the horizon stretches on, and on, and on. The physics that we believed were absolute are proving to be merely local approximations, specific rules that apply only to the quiet, late-stage universe we happen to inhabit. When we look further, when we look deeper, we see that the universe does not care for our textbooks. It follows its own path, guided by forces that we are only now beginning to sense. This discovery invites a profound change in our collective mindset. It forces us to accept that the most important answers are often found in the things that don't make sense. When the data clashes with the theory, we shouldn't shy away from the contradiction, we should lean into it. The impossible galaxies are not a failure of our technology, they are the ultimate success of our exploration. They are the heralds of a new age of discovery, one where we are willing to let go of our most cherished certainties in favor of the truth. We are learning that the universe is not a finished product to be solved like a puzzle, it is an ongoing, evolving, and fundamentally mysterious process that invites us to keep looking, keep asking, and keep wondering. We must hold on to this sense of wonder, even when the foundations of our knowledge seem to be shifting under our feet. For the scientific journey is not about reaching a final, unchanging set of equations, it is about the constant, rigorous, and beautiful pursuit of what lies just beyond the veil. The James Webb Space Telescope has gifted us with the vision to see that the universe is far older, far more active, and far more miraculous than our early maps suggested. We are standing at the threshold of a new cosmology, one that embraces the impossible and uses it as a stepping stone toward a greater understanding. We are part of this story, a brief flash of consciousness in the vast, ancient, and ever-expanding mystery that is the cosmos. As we move forward, we carry with us the knowledge that even if the physics break, our capacity to observe, to reason, and to dream remains intact. We will continue to look into the deep, dark, and beautiful void, waiting for the next whisper of light to tell us the next part of the story. The journey is far from over, and the greatest discoveries, the ones that will truly define our understanding of existence, are still waiting in the shadows of the stars, waiting for us to find the courage to look at them, to understand them, and to grow because of them. This journey of discovery is a collective endeavor, a testament to the insatiable human need to know the unknowable and to map the infinite. Whether or not we ever find a single, unified theory that explains it all, the act of searching, of analyzing, and of admitting when we are wrong is the very heart of the scientific endeavor. We are the witnesses to the unfolding of time, the observers who give meaning to the silent dance of the galaxies. We have been humbled by the size and the age of the universe, but we have also been empowered by the realization that we are capable of seeing, understanding, and adapting to the impossible. As we continue this mission, let us remember that the universe is not just a collection of matter and energy, it is a source of infinite wonder. We have only just begun to understand the early pages of our story, and the chapters yet to be written will surely be just as challenging, just as surprising, and just as magnificent as the ones we have just explored. Thank you for your support.